give you guys a chance to ask me any questions about anything that you might have not understood clearly in class, or anything that you've come across since you've left class and been studying on your own. But effectively, there are some calculation questions that have to do with grounding and bonding. And what is weird about them is that one of them is the new table in 250, which is, and pardon my handwriting, it's hard for me to write with a mouse, so you just have to forgive me. But it's 250.
Okay.
That's about the best I can do. 250.102C1. It's on page 124.
Right.
All right.
You had to write neutral above it in our class.
Huh?
You had me to write neutral above it in our class.
I did. I had you write neutral. Okay. So I have somebody else that's got that says they're on iPhone, but I don't see anybody on the picture, so I don't know if they're there or not. But the only people I hear. Huh?
Yeah. Oh, that's my phone. I don't want to put my phone on. I'm afraid if I lose it.
Okay. No, that's fine. That's fine. No. You can leave it on. I just want to make sure I wasn't missing anybody.
Yes, sir.
I'm sorry. Give me 1 second. Okay. So on page 124 is where we're at. It's a table that looks really eerily similar to the 250.66, which is on page 121. So I want you to look at page 121 first, and then keep your hand there on page 124. And let's just compare these two tables real quick, right?
Yes, sir.
They look a lot like the same table, but the big difference between .66 and the new table is that we used to use .66 to size the neutral conductor. The problem is that we had a math problem in the code book. Let me see if I can type this better than just see here. Hold on, let me see. Insert a. All right, so we had a rule that said if we have a conductor, it went off my edge of my screen there. Conductor that was larger than 1100. What's the largest wire size that you see on the bottom of page 121 on the table there?
121. Largest wire in copper 3.
No, all the way down to the very bottom of that table. It goes over 1100.
Yes, sir. Yes. Over 1100 on copper. Yes, sir.
All right, so that table basically stops at the 3/0 that you're seeing there on the bottom.
Okay.
It is 3/0 on the bottom, right?
Yes, sir.
That's on. I mean, you're on page 121, 250.66.
Yes.
Okay. So the largest wire size that you ever have to have as a ground electrode conductor, which is your service ground, right? Is going to be that 3/0 size. There's really not any requirement to have anything larger than that as a ground wire. The problem is that we were using this table for also sizing our minimum neutral conductor size, because it was the only table that we had. So if you go and look at the note 1 at the bottom, note 1 has to do with parallel sets of conductors on 250.66, note 1 at the bottom. It just says basically there's some math that we're going to do, and I'm going to explain all that to you here in a minute. But just so you understand, that note 1 at the bottom of that table on page 121 has to do with parallel sets of conductors. When it comes to the wire size, once we reach 1100 kc mil on the table that you're looking at right now, there is no other wire size that is going to be required larger than a 3/0 GEC. It's the max. Okay?
Yes.
All right, now if you go back now to page 124 and look at the new table. 250.102C1.
Mm-hmm.
So basically now, if you look at the bottom of the table, it ends in 2-aught or 3-aught. What's the largest wire size there in the bottom?
2-aught.
2-aught. And what's the largest wire that's equivalent to that 2-aught? 1100?
It's well, on this one right here, and I'm not doing it right, it says over 600 to 1100.
Right.
So, yeah, now over 11 to 750 C note.
Say the last one again.
No, very bottom of it says over 1100. It's just C notes.
Right. Okay. But the actual table has 600 to 1100, right?
Yes, sir.
Okay. And then the largest wire size you see on that table is a 2-aught.
Right.
Here's the big difference. That table doesn't stop like the other one does with the 3-aught conductor. This table actually has a math problem in note 1 that has to do with sizing conductors that go off that table, basically. In other words, if I have a conductor larger than 1100 kc mil, what I have to do is I have to do a little bit of math to it, and then I can't be less than 12.5% of that largest ungrounded conductor.
Right.
So in other words, I may have a 2000 kc mil conductor, and I would actually have to do the math of 2000. Now let me see, can't be less 12.5%. All right. So if we had, for example, a 2000 kc mil conductor, I'd be looking at a value of 12.5% of that number. Do you have a calculator handy?
Mm-hmm.
All right, so if we had 2,000 circular mills, 2,000 kc mil, that's actually 2 million circular mills, right? Because the K stands for another 3 zeros.
Right.
If I multiply that wire size times 0.125 for 12.5%, that means that my GEC can't be less than or small, excuse me, not GEC, I'm sorry, wrong word. My neutral conductor or my system bonding jumper couldn't be less than 250,000 kc mil. And that's a much larger wire than where the other table stopped at that 3-aught. Does that make sense?
Yes, sir, sure does.
All right, so the big difference is that because we were limited with that other table and people were getting it confused, sometimes guys were trying to take this 12.5% business right here and trying to apply that to the grounding electrode conductors, not understanding that this is a neutral calculation. It's got nothing to do with the grounding electrode conductor size. So they separated these two tables, even though they look real similar. They separated them into two separate tables so that we could have one dedicated to our neutral conductors with the special math that you're looking at with note 1. The other one is just a normal table with the regular notes that it had from before. So that's why I had you mark on there on the top of that table, minimum neutral conductor size. I mean, that's basically the best way to look at it.
Okay, I got one more quick question for you.
Okay.
If that was, in other words, that was worded into a question that you come across, and it would ask you that, then you would go to for your neutral.
Yeah, let me. I wanted to explain the table and kind of explain the math first. I'm going to give you some examples of what he ran across on his test, and it'll help make more sense here in just a second. I've not seen them actually use this table to size a neutral conductor. What they're using it for is to size a system bonding jumper. And if you look at the top of the table, all of the other conductors that are, and I'm on page 124, right?
Mm-hmm.
So all the other conductors that are listed on that at the top of that table are all something jumper, system bonding jumper, main bonding jumper, so on and so forth. Okay. All right. So you kind of understand this so far. Let me give you an example question real quick, just to see if you can make sense of this. If I had a conductor sized as a, let me insert text here. All right. So if I had a conductor that was sized as a 1200 kc mil, what would be the minimum size neutral conductor? And I'm not going to use the word neutral because they don't use the word neutral. They use the word grounded conductor on the test. So I'm going to use that here. But remember that's a neutral. It's not a grounding conductor. That's a grounded conductor. So. All right, and that's assuming that your calculated loads are going to be less than this calculation. If your calculated loads are more, then this calculation would not be used. It would be whatever your calculated value size would be based on whatever wire size you manually calculated out. So you would just have to always keep your load requirements in mind. This is just a minimum size, notwithstanding load calculations. All right, so 1200 kc mill, do the math for me real quick and tell me what does that come out to be? So on your calculator, what are you gonna do?
I'm going to put down I'm going to put down 120.
Yeah, it'll be 1200, and then just instead of the K, put 3 more zeros on your calculator. So it'd be 1.2 million is what, or 1,200,000 circular mills. Can you see my screen?
Yeah, I got you. Yeah, I got you.
Okay. All right, and then what are we going to multiply that against?
I guess 12.5%.
Yep. So 0.125.
Give me 150.
150,000.
Yes, sir.
All right. Now here's the rub. I can't tell you off the top of my head what size a 150 kc mill conductor is. I know most of the smaller wire sizes, but you get into 3/0 and 4/0, I don't know those. So to find the correct wire size to match up with that, what you want to do is go to table 8 on page 766 of your code book. It's chapter 9, table 8.
Yeah, I got you.
Okay, so the third column that you see on that table on page 766, those are circular mills. What's the next wire size bigger than 150,000?
3/0.
3/0. What is a 2/0 size?
2/0 is a 133, 100,
Okay.
and then the 3/0 is 167, 800.
All right, and that's going to be exactly what we'd have to have then, which would call that a 3/0.
Mm-hmm.
And there you go. Okay.
Cool.
All right, that's if you have one wire, right? One set of feeders, one wire.
Mm-hmm.
All right. What do you do if you have parallel sets of conductor? And so let me kind of paint a picture here. Now I'm gonna use this same example with all of the tables. Okay, so we're gonna take a pause real quick, and we're gonna leave this table, and we're gonna go to the table on page 121, 250.66. Okay. All right, so we had. Let me do that really. We had a second ago, we had a table that was dealing with the grounded conductor size. This is the grounding conductor size. So this is the minimum size grounding electrode conductor, your main service conductor, ground. Okay?
Mm-hmm.
Now, if I had a 1200 kc mill conductor in one pipe, you know, like an A phase, a B phase, and C phase is 1200 kc mill each, I would just go straight to that table. There's no math. I don't have to do the 12.5% or anything. And what size wire would I put on that according to the table?
You put 3/0.
Yeah, that last line says what? Hey, Casey.
Huh? Over 1100. Over 11 is 3/0.
Okay, and that's it. There's really any wire size larger than 1100 is going to be a 3/0. That's the maximum size. There's no math involved. We're good, right? All right, now if we have an issue like this where we've got parallel sets of conductors and we're sizing our grounding electrode conductor. Hey, Casey, how are you?
Pretty good, sir. How about yourself?
Just fine. I'm glad you could join us. Sorry for the delay. I apologize tremendously, but I'm glad you could make it.
Thank you, sir.
I'm going to try to email these slides that I write on to everybody after this class is over with tonight. Plus, I'll post this video on YouTube so you guys will have a chance to review it again at your leisure. So you should have some more access. And if anybody has questions after this, don't feel afraid to ask later on. We'll do some one-on-one or do what we need to do to help you. All right, so we're sizing a GEC based on parallel sets of conductor. Give me just a second, I'll make that all fit. Okay, let's say that we have, since this table is based on one wire size, right? If I've got a pipe like this that's actually got 3 separate parallel identical sets of feeders, and I'm trying to size my ground electrode conductor, well, when we do the math up here for these feeders, the reason why we split them into parallel is because we didn't want to have to run as big of a wire as we would normally, right?
Mhm.
So, but when I do that, I'm still dealing with the same wire amount basically and the same ampacity. I'm just dividing my wires into smaller sets so I can subdivide that load across more than just one wire. So I'm going to have in each one of these pipes, I'm going to have like an A phase, a B phase, and a C phase. And let's just say these are all 250 kc mil, just to make it easy, okay?
Mhm.
All right, so we've got 3 parallel sets, 250 kc mil conductors. So in this pipe right here, I've got a 250, a 250, and a 250. All right, if you look down at note 1 now, note 1 says where you're running these things in parallel, what you have to do is some fuzzy math. So we basically have to go over here and we're going to have to take the size of this A phase, which is 250, and we're just doing one pipe. We're just looking at one single leg of this 2-phase. Sorry, again, it's terrible when it comes to trying to draw with a mouse. That's A phase, right?
Yes, sir.
And then I've got B phase right here, which is also a 250 kc mil. And then the same thing over here for C phase, I've got one more 250 kc mil. So I'm going to add all 3 of those together. I'm going to take 7. I'm going to basically have 250 times 3.
750.
That's going to be 750. And what I've done is I just kind of falsely re-added them back together is what I'm doing, so that I can then use that net math size that I just came up with and go to the table and apply the table based on that wire size. So I'm going to do times 3, and that's going to give me the 750, and that's going to give me the wire size I would actually use to size the GEC inside this one pipe. I'm going to use 750 kc mil on that table, and what would that give you at 750 kc mil?
2-aught.
2-aught. So right here in this pipe, I'm going to have a 2-aught conductor based on that fuzzy math right there with note 1. And Casey, I see you're kind of getting settled. We're on page 121 of your code book, okay? You turned your your mic off, but that's fine. Okay, I can hear you now. Oh, well, there you go again. Either way. All right. And I'm going to do the same process, obviously, 3 times because everything's going to be identical. So effectively, I'm just doing it one time and then just repeating it all the way down. So I would have a 2-aught in this pipe. I'd have a 2-aught in this pipe. I'd have a 2-aught in this pipe. I'd have a based off that same math. That makes sense?
Yep.
Sort of? I went kind of fast, so don't be afraid to say it doesn't make sense.
Yeah, no, I got the parallel part.
Okay. All right. So what would you do if you had the same kind of question on your test, but instead of giving you a 250 kc mil, they gave you 3-aught conductors? So you had 3 sets of 3-aught, 3-aught, not kc mil. So you've got 3 sets of a 3-phase 3-aught conductor. So in this pipe right up here, what I've got instead of 250 kc mil is I've actually got, oops, I didn't mean to do that. I've got a 3-aught, 3-aught, 3-aught. So size those 3 pipes based on these 3 wires being a 3-aught conductor. So what are we going to do here? How do you add 3 3-aughts together?
Well, what I've done, right, I went to the table 8 and got a circular mill.
Beautiful, man. I'm proud of you. That's exactly right. Exactly right. Anytime you mathematically have to manipulate an American wire gauge size, you got to convert it to circular mil. So that's awesome. That's exactly right. So you go back to page 766, right?
Yes, sir.
And what is a 3-aught conductor? Is it 167?
You're 167, 800.
167, 800. And I've got 3 of those suckers, all the same size. So I'm going to take 167, 800 3 times. And I'm going to let you do the math and tell me what that is. One 167,800 times 3. What does that come out to be?
167,800 times 3 is 503,400.
503,400?
Yes, sir.
Like 503,400?
Yes, sir.
Okay. So that is a 500 kc mil conductor, but we just missed that. So we're actually going to have to round that up to the next larger wire size. So to convert that back on the table, that would be, what is it, 600 is the next wire size?
All right, well, okay, with circular mills on table 8, it goes up to
The 4-aught.
4.
And then after that, if you look to the far left, the very first column, we start expressing the wire sizes in circular mills after 4-aught. So a 250 kc mil is 250,000, so on and so forth.
Once it jumps to 250, they're talking about circular mills on the
That's right.
side.
Yep. So a 250 kc mil is 250,000 circular mills. So they just,
I got you.
yep.
The equivalent of 500,000 mills. So since we're over, do we go to 600?
Yes, that's right. So based on this math, right?
So, yeah, I got you.
The next equivalent wire size would be a 600 kc mil. Does that make sense?
Yep.
Now I go back to the table on page 121 and I use a 600 kc mil to apply the table size.
1-aught.
For 600 kc mil, be 1-aught?
600, yes, sir.
Okay.
No, it's 350 through 600 would be 1-aught.
Okay. You're going to laugh at me, but I don't even have a code book in front of me, so I'm just doing this from memory. That's why I keep asking you questions to make sure I don't forget what's on the table. But at any rate, you understand what we're doing here, right? The parallel sets of conductors. So there's some fuzzy math. If I'm sizing a grounding electrode conductor, that's different than my neutral calculation that's on page 124. This is my ground wire at the surface, my main grounding jumper, or my main grounding electrode conductor. So if I have parallel sets, I'm going to add the 3 phases together, the A, the B, and the C, in one pipe, and then I'm going to use that fake wire size that I came up with and apply the table based off of that wire size. And then I'll have a full, whatever that table value would be in each pipe. So in this case, we'd have a 1/0 in each one of the 3 sets.
Okay.
Okay? So far, so good, right?
Yes.
All right, now let's talk about parallel sets of conductors that are for your system bonding jumper or your main bonding jumper where those are running parallel. So let's go back to page 124 real quick. So we're going to go to, and I'm just going to put system bonding jumper just so that it's shorthand. Based on parallel sets of conductors, let's do 3 sets. We'll go back and do the 250 just to make it easier on ourselves just for a minute. So if you look down at the bottom, remember that note 1 on that table has that 12.5% business, right?
Yep.
But it's real similar to the other table because it first tells you to do the same fuzzy math. You have to take all 3 phase conductors, all the 3 hots, and you have to add those up first, and then take 12.5% of your wire size that you came up with.
You just got to add one wire in each pipe.
Well, we're gonna do one set, right?
Yeah.
Does that make sense?
Mm-hmm.
So if I've got 3, huh?
Yeah.
Do what?
No, I took, you're talking about one pipe.
So if I had 3 pipes, right, of 250 kc mil conductors, 3 sets, and each one of those pipes had 3 250 kc mil phase conductors, an A, a B, and a C. Make this one red. That's my A phase. And then my B phase, we'll call it black, or, well, in Austin it would be black. Don't make fun of me. That's a hell of a big service for a single phase, for a 240 volt system, but you get the idea.
Mm-hmm.
And the other color is going to be blue, right?
Yeah.
So I've got those 3 conductors, a red, a black, and a blue, all in this pipe. And I'm going to size this based off note 1 on the page 124. That means that I've got to first take these 3 conductors, the A, the B, and the C, and I got to multiply them times 3, or add them up. 250 times 3.
Right. Give you 750 again.
Yeah, give me the same 750. Here's where we differ then. Instead of using the wire size and going straight to the table, now we have to do that 12.5% business again. So I have to take the 750 kc mil, and then I have to multiply that times a minimum of 0.125%. And I'm doing it just 0.125. I'm not doing the 1 in front of it because I want to know just what the...
On this note 1, it says that don't have any of the multiplication was over 1100 kc.
Oh, yeah. Yeah, you're right. Yeah, we're not over that with 750. You're right. Yeah, you can go straight to the table. You're right. Yep. Yeah, it has to be over 1100 kc mil. So you're right. Let me change this. Thanks for catching that. We'll make these 500 kc mil. How's that?
That works.
That'll give us a wire size large enough to do this. You're absolutely right. What he said, Eric. I mean, we lost what's his name? Sorry. What you said was, if it was a 750 kc mil like I had it, you could have gone straight down to the table and sized it. What would it have been at 750?
At 750, it'd be 2/0.
Be 2/0. So that would have been the answer, right? We'd had a 2/0 in every one of the parallel sets of conductors. All right, but if we go over the 1100 on the table, we had 3 sets of 500 kc mil, did the same math.
1500.
Or 1.5 million times 12.5%. So we'd have 1,500,000 times 0.125. 187,500 would be our size.
Right.
And then I would go back to the table. back there, and that's going to have to be a 4/0 because 3/0 is just 167. So you go back to page 766.
Yeah. With 4/0.
It'd be a 4/0. Okay.
Yeah.
So what this guy was telling me was that he had 3 questions on his exam that all were just like the example that we just did. Basically, they're phrasing it as a bonding jumper or system jumper, and you're sizing a jumper based on parallel sets of conductors. So they'll give you 3 pipes just like this, or they give you a wire size, and in my case, I gave you the 500,000. I don't know, he couldn't remember the exact wire sizes that they gave him, so I'm not going to try to remember, but I think they were 600 kc mil, if I'm not mistaken. But the mechanics, regardless of what wire size they give you, are going to be just like that. Okay? Okay, we got one more table to look at, and that's the one on page 131.
$131?
131. It's 250.122.
Okay.
Um, 250.122. Okay, so this is your equipment grounded conductors, right?
Yes, sir.
And so this is a little different. This is not it's a ground wire, but it's a branch circuit ground wire is what we're dealing with here. So it's not really the same as either one of the things we just looked at. We're going to call this 250.122. We're going to call this our branch circuit ground. The technical term for it is EGC, equipment grounded conductor. Okay? And so you should have had EGC written on the top of the page, on the top of that table on page 121, excuse me, 131, right? And you should also have a note to yourself that that's branch circuit grounding.
Right.
Okay? This one is the table that's right there. It's based off of breaker size. So if I were to have, for example, a branch circuit overcurrent device, overcurrent protected device, we'll call it OCPD, sized as a 70 amp device, call it a fuse. What would be my minimum size EGC based on a 70 amp fuse or breaker for that matter?
Number 8.
Okay, so you got down to the 60 amp, which says number 10.
All right.
Anything larger than that all the way to 100, which that's where this would fall in, would be a number 8, and you're absolutely right. Okay? All right. Now, there is a rule for parallel sets of conductors when it comes to branch circuits, but it's basically a full size. There's not really any kind of discount when it comes to branch circuit conductors or branch circuit grounds. So if I had 3 parallel sets of conductors running off of a breaker, going to a sub panel, let's call it, and we're calling these branch circuit, even though they're feeders, they're still branch circuit feeders because they have a breaker in front of them, right? So we've got a main MDP or something of that nature. May have a 500 amp breaker there, and then we've got 3 sets of parallel conductors coming off of that going to some other load center. That's kind of the example that we're talking about. So if we had a setup like that, we had 3 wires in here, and the wire size were 250 kc mil, just like the other ones were, right? So we had a branch circuit with 1250 kc mil, 3 parallel sets coming off of a 1200 amp breaker. All right, well, this table is based off a breaker, not a wire size. So in this case, we don't really care what the wire size is. It's all about the breaker size. So if these things were coming off of if these things were coming off of a branch circuit that was sized with a 1200 amp breaker, 3 sets of 250 kc mil, paralleled off of a 1200 amp breaker, there won't be any discount at all whatsoever on those wires. So I'm going to have whatever that table value is for a 1200 amp breaker.
3-aught.
I'm going to have a 3-aught then in each one of these 3 parallel sets of conductors. There's no discount. I have to have a full size equipment grounding conductor in every one of these legs in case somebody cuts through 2 of them, and so I can still clear the entire ground fault or signal that I need to carry back to that overcurrent device to trip it. So I don't care how many parallel sets there are. I don't care what the wire size is. I only want to know what size is the breaker. And as simple as that, whatever that table value says, that breaker size is what matches up with that breaker size. I'll have that full size in each parallel set. No discount. Make sense?
Yep.
All right.
Not giving you the breaker size?
No, not when he's asking when they ever give you a question without the breaker size, and that is a key word to that question. It has to have a breaker size for you give them that bracket.
Absolutely. Now, what they will do sometimes is they'll give you a breaker size and a wire size, and you have to be careful because the breaker size doesn't matter to you when you're doing the GECs or the bonding jumpers, right? Those are based off a wire size.
Right.
And sometimes they'll still give you a breaker size. Huh?
Which would be 2 separate questions.
Absolutely, yeah. But he's right. On a branch circuit EGC, they'd have to give you a breaker size. Otherwise, there's nothing you can do to size it. But, I mean, you could probably, I could see where they might write up a question where they gave you a set of conductors, and then you would have to assume the ampacity of them and then size the breaker based on that ampacity, but you'd have to have a breaker size ultimately to do that. Okay?
Okay.
All right. Any questions?
Nope.
Let me cover this again real fast. I'm going to give you a couple of example questions, and you're going to just tell me what size it would have to be for each one of these, okay?
Okay.
So let's say that we had, let's see, insert, sorry. Give me one second, let me get this slide set up. So where's my, sorry, give me just a second, sorry about that.
Yeah.
All right. Here we go. That's what I was looking for, layout. So if we had a ground electrode conductor, and they were asking us, given a set of ungrounded conductors sized as 3-aught aluminum, what size minimum grounding electrode conductor would we need Now, I told you that the feeders are aluminum, but I didn't specify that I wanted my GEC sized in aluminum, so you're still going to answer in copper, okay? They have to specifically ask you for aluminum on both of them for that to matter. Now, I'm going to use the aluminum column on page 121, but I'm going to answer in copper unless they flat out specify that the GEC itself is also aluminum.
Number 4?
And that's copper? I think that's right. Like I said, I don't have the table in front of me, but it'd be a 3-aught.
Number 4.
So it's on the second column, right, on the aluminum?
Yep.
And then two places to the right, or yeah, you'd have copper. Or no, one right next to it would be copper.
Be number 6 copper.
Be number 6, okay.
Yeah, you said yeah, but that's 3-aught, right?
Right, aluminum.
Aluminum, yeah. 3-aught aluminum. Be number 6 copper, right?
Yeah, that sounds right. And I'm going to answer in copper unless they also, if this question would have said what minimum size aluminum grounding conductor, then I'd put, what is it, number 4?
Number 4 for aluminum.
Then I would answer number 4, but they have to tell me both this and this. Otherwise I would just assume this is copper. Always think in terms of copper unless they tell you specifically otherwise. All right, so now, huh?
I guess it's a stupid question, but when you're pulling, I know you said they use that rule of thumb because of copper, but usually when they pull aluminum, you do that, number 1, because of cost difference. Why would you assume that it would be the copper when you do the ground when they ask for aluminum?
Here's the answer to that. It's a really good question, okay? I'm not saying that in the real world we might assume one way or the other, but a lot of times we run copper GECs anyway, even if we run aluminum feeders. But if you look in 110.5 in the front of your code book, 110.5, what's the heading of 110.5 say?
The conductor normally used to carry current shall be copper unless noted otherwise.
So it's an umbrella rule, and PSI uses that, right? So in the code book it says unless we specify it's not copper, it's going to be considered or assumed to be copper. So the answer to your question is they're just playing a game with you to make sure you understand that article and that you would catch that trick.
Yeah.
Okay. And I can tell you it's a fair trick because, I mean, you know, we do have to assume copper, you know, in all cases, unless we really know what we're, you know, trying to accomplish with aluminum. But at any rate, it's just one of those things you just got to be aware of. All right. Given 4 parallel sets of 4/0 copper conductors in separate pipes, what would be the minimum size GEC in each conduit? So I've got 4 separate pipes. Each one has got 3 4/0 phase conductors in it.
Yeah, you take your circular mills, your 4 times 4.
Yep, and that's, what is it, 433 is it, or what's, I mean, not 433, 230, what's the 4/0?
The four circular mills
Uh-huh.
was 21, 211, 600.
Each. Times 3 of those.
Yes.
So we'd have 6, 34, 18.
Yeah, but you got 4 parallels though.
Yeah, but remember, the number of sets is really kind of irrelevant. We just look at, yeah, we just look at the ones in just one pipe, and then everything else is going to be the same, you know, mirrored set. So I'm gonna do 20 211, and I got that from page 766. That's the circular mills on table 8. So 211 600.
634,800.
Circular mills. Right? Now what do we do?
So you can go to 7 off of the,
Well, what's the next larger wire size from 634 800? The 700 or 750? Or is there 650?
no, there is no 650.
So it's a 700, right?
Yeah.
So we're going to basically round that up to the next larger wire size, which would be a 700 kc mil. And
Right.
then, huh?
I'm agreeing with you.
And then I'm going to go back to the table and use the 700 kc mil as my wire size to apply the table value.
Then you go back to,
Page 121.
what page?
121.
What one there you go. And 750.
700. Huh?
2 off.
2 up. And I'd have 4 2-aughts, 1 in each one of those parallel sets. Okie doke.
Okay.
That makes sense?
Yes, sir.
All right. So if I were to take, let me move this out of the way so I can see what I'm doing here. If I were to take the same questions and instead of doing GECs, they asked me for a system bonding jumper. I don't know if it's system bonding jumper or main bonding jumper, or what's the other bonding jumper they have listed on the table?
You got a main bonding jumper, a system bonding jumper, a jumper, and a supply side bonding jumper.
Okay, it's the supply side maybe. The key word there is the word jumper, right? I mean, that's going to be your yeah, that'll be your clue. So, I mean, if you see that, you'll know what table that they're dealing with, right? All right, so we're going to just trying to get this stupid. There we go. All right.
So if you was using the same calculation, which would have been the 750, you would put it at 2 off.
Yes. Well, let's see. So we had, sorry. So we had 4 parallel sets.
Mm-hmm.
What was it, 3-aught or 4-aught?
Well, the 1200 amp is irrelevant in that question, right?
That's exactly right. The 1200 amps got nothing to do with it. And sometimes they'll put it in there just to try to mess with your mind. But
So
it does.
Let's say 750, right?
It'd be the same 750 because we convert that 4-aught back on table 8 to 211 600 each times 3 would give us the 634 800. Round that up to 700 kc mil. So then we'd use a 700 kc mil, just like we did on the other table. But we'd go straight to the table and apply that, whatever that wire size would be. Is it 2-aught?
2 off.
Okay, so that's the same as the other one was, wasn't it?
Yep.
So, all right, now one more question. 3 parallel sets. of 1,000 MCM would have what size minimum system bonding jumper? That M is the Roman numeral for 1,000. So we used to call wire sizes MCM. Now we call it KCM because that's the System International metric equivalent to the Roman numeral M, but it's still the same thousand. So a 1,000 MCM or 1,000 KC mil would still be 1,000,000 circular mils. Which would give us a total of 3,000,000 circular mils. And then we go down to the table, and what do we do with the with this table with the note 1?
You're gonna multiply it by 12.5%.
12.5%. So this is on page 124, note 1 to 250.102C1. I would have to multiply that 3,000,000 KC mil or 3,000,000 circular mils by 0.125. That's 12.5%.
375,000.
375,000. And that would be too big for a 350. So we'd be looking at a 400. Is it? Yeah, 400 KC mil conductor.
Oh, go back to your time, get that.
Huh?
Yeah. You go back to that table to find out the 400 KCM.
Yeah, you could. I mean, either way.
Yeah.
But that 400, is it 400 or 450? 400, isn't it?
400.
So it'd be a 400 KC mil, but that would be the minimum size system bonding jumper. That's not what we use to size the table. We're at 400 KC mil now, not too off.
Right.
Okay, and that's the difference, is that because of that math down there, you've got a lot more room to have much larger wire sizes than you ever could have had with the other table, the GEC table. Okay?
Okay.
And then if we had finally one last example. No, that's not what I wanted to do. Trying to do a new slide there. Nope. All right, so if we had this last one, they ask us for a equipment grounded conductor. Right? And we had the same four parallel sets of 4-aughts that were running from instead of to. What would be the minimum size EGC required in each set?
3-aught.
So again, you don't worry about the wire size. You look straight at that 1,200 amp breaker. Go to the table on page 131, and what's it say on a 1,200 amp breaker on copper?
3-aught.
3-aught copper conductor. And there'd be one full 3-aught size in each parallel set. So I'd have 4 3-aught EGCs. Make sense?
Yep.
All right. That's all I had to cover with you guys. You guys have any questions for me on anything?
Yes, I do.
Okay.
On my, did you ever get a chance to look at my Ohm's law that I texted?
I started looking at that.
Do you have that question? There's one that I changed my answer to. And I'm just kind of curious if I changed the right one or not.
Which one?
On the second page of the Ohm's law where it asks in a parallel circuit rated at 120 volts, you have a 12 ohm resistor is turned up to a 9 ohm resistor. What's the voltage drop for each resistor reporting? And I had marked 69 and 51.
Which page? I'm sorry. Which page is it again? The first page or the second page?
Yeah, I'm sorry, page 37.
Okay. Okay, which one is the top one or the
The second one on page 37.
second one? All right. So the thing to remember about voltage drop is there is no voltage drop in parallel circuits. I mean, there is. Don't get me wrong, but that's that 3% business or that 5% business, over 300 feet down the long stretch of conductors. But when we're talking about voltage drop as it applies to Ohm's law, there shouldn't be a voltage loss across a resistor. It should be the same voltage across each leg or each point in a branch circuit. That's the magic of a parallel circuit, is we don't lose our volts like we do in series.
Well, so the answer that I sent you was like that 69 volt and 51 volt, but I went back last night and recalculated and come up with 0 and 0. So
that's right. That you caught it then, because the answer to that would there would be 0 voltage drop or voltage loss across those resistors in parallel. Okay. So it would be 0 and 0.
Now, quick question, and you tell me if it's hurting me. Oh, something, like I said, I don't deal with calculations as much because our line of work is all figured out. Is looking at other YouTube or online calculations, would that hinder somebody that's trying to learn and to remember how to do it, or is that a good thing?
To go online and
it's like getting a lot of calculations and stuff in your head at first, and then it starts.
Let me see if I can rephrase what you're asking me to make sure I understand what you're asking me. So you're asking me, would it hurt to go online and look at some other stuff?
You froze up, you there?
Sorry, I'm still here. Can you hear me?
Yeah. Well, no, what I did was, I went to the calculations and I used your formula, and I guess needing that 101 to kind of help me comprehend it.
Sure.
I went to some videos online and grasped the concept of no voltage drop in parallel. For what you're teaching us right now, is it more of a hindrance for somebody to go online and look at different illustrations? Yeah,
I did understand what you're asking. So the bottom line is, it's not an easy question to answer. I don't think it harms you to go look at other videos and see other, because I mean, Lord knows I've done the same, and I've learned plenty, online in my career by watching Mike Holt, some other stuff like that. The problem is when you get into specific types of code calculations on this Texas PSI exam, because of the use of exceptions. And so if you're looking at how to size motor conductor or motor overcurrent devices, or if you're doing any kind of size and breakers in certain cases, it could harm you because they're going to take an exception if they can normally, just like you would in the field. But on this test, you can't. And so that sets up some real odd rules that we have to have just for this test. And so, I mean, I've got some video stuff online that you're welcome to look at. But if you want, I would rather do one-on-one sessions with you. I mean, this has been great. I wanted to get my topic off, my chest tonight, because these are things that I know you're about to be facing on your exam, and we didn't really cover them in class. So I wanted to do that tonight. But the Ohm's law stuff, why don't you and I do an Ohm's law sometime, either maybe Sunday or possibly next week early, so that you don't have to sit on them too long, and let's do another one of these sessions just like that. Can we do that?
Yes, sir. Because like I say, my name is Jake. I want to pass this thing while I'm taking.
Sure.
Looking for the question code book I can do. It's a calculation I feel that's going to be my biggest hindrance, and I want to be able to not only have it to pass the test, but I want to know it. I can go in there and do a few of these and figure it out. But I want to do after my master's, I still want to be able to brush up on it, because like I said, we don't use it that much in what we do.
Okay.
It's commercial.
Yeah, I hear you. Given a let me ask you a quick question. Given a 3-phase 50 horsepower squirrel cage motor operating at 480 volts, right? Calculate if you don't mind, let's just make sure that you don't have any issues with. Can you see that all right? That big enough for you?
Yeah, I got it.
Sorry, it dropped out on you. Give me 1 second.
No, it's all right. Would it be number 4?
On number 4? Okay, so what do we have? What's your FLC value on page 351?
It's 77 on a 50 horse. At 460 volts or 480 volts is 77. I'm
Yep.
sorry,
I'm sorry, it's how much?
65.
65 amps, right?
Yes, sir.
And then for the conductor size, what multiplier did you use for that? The size that.
Number 6. I told you 4, but 6.
Well, but what did you do with that 65 amps? Did you multiply it times something first, or?
No, but I need to multiply it by the 125%, right?
125%, that's right. Yeah, because we're looking at that motor is going to be considered a continuous duty application, right? So we multiply that times.
81.25.
Huh?
81.25.
1.25, yeah.
Yeah.
So multiply that times 1.25, and that would give me 80 what?
81.25.
Thanks, sir. and I would go to page 161.
Yeah,
I'd use the 75-degree column.
yes, sir. And you got 65 at number 6 and 85 at
Number 4. Okay, what about the fuse, the non-time delay fuse element?
A time delay fuse for, let's see, what is it? Yeah. The code,
So I'm going to start with the same exact process. That's going to be,
when you go to 85 amps, and you want to see the same,
well, it's not 85 amps. To go back to the 65 amps that the motor is rated for, right, on the FLC value,
yes,
right?
uh-huh.
And then what do we do?
You gotta go over to that table where it's, has the non-time delay calculation on it.
Yep. Page 335. It's 430.52.
So you take, 65 amps.
Times 300.
300.
Be 195.
Yes, 195.
All right, now expect that the answer block would look like 195 amps as one answer. Then there'd be a 175 amp as another answer. Then there'd be a 200 amp as an answer. And then there'd probably be some crazy large 600 amp or something crazy. Who knows what the last one would be. Of those 4 answers, which one do you think would be the correct way to approach it?
Well, you gotta go to where it gives you the, record sizes.
Yep,
Notebook.
page 96 and 97.
Yeah, page 96, 97, and 200 amp.
So are we rounding up or down?
Round it, I'm going to round, I'm sorry, it's, 175.
175. All right. Now that's the whole point, right? What you're asking me, my Colts would probably tell you to go put a 200 amp non-time delay fuse on that, and he would be right. If I was doing it in the field, that's exactly what I would do, because I'm allowed to take exception number 1 on page 335. 430.52C1, exception number 1 allows me to round up on a breaker for a motor. But on this Texas PSI exam, exceptions are not allowed, period, unless they tell you specifically to use them.
Right. I got you.
Yep, so we're rounding down based off of that arbitrary rule. So as long as you can keep the little things like that in mind, which there's not that many of them, but there are enough of them that, if you didn't know them, they'd probably cause you some headaches. But as long as you keep those basic rules in mind, you'd be fine using anybody's material online as long as they knew what they were talking about. I have seen some stuff online that they honestly didn't have a clue what they were really talking about. So
So how often with this one-on-one session with you?
how often do I do these one-on-one sessions?
Yes.
I do.
Actually, I enjoyed your class, but I got more out of what we just did one-on-one on calculations than I did. I don't know if it's because of the, not really wanting to speak up in class.
Yeah.
I don't know if that has anything to do with it or what, but I got more out of this comprehension than what not getting nothing over your teeth, but
No, I feel you. It's kind of weird to try to ask questions, especially in a class, and the pace of the class is a certain thing, and you're just trying to keep up, and so sometimes guys just don't like to ask questions in the middle of a group anyway. So I totally get that, and there's nothing wrong with that. I'm glad you got something out of this, and I don't mind doing them. The answer to your question is I do them as often as I can fit them into my schedule. And that's
Well, and that's what I mean. It just whatever it fits in your schedule, any time. I enjoyed the one-on-one. I get a lot from it.
okay. Well, like I said, if you'll text, I'm sorry.
I said I'm still following through with the workbook stuff, but you know, I try not to get held up on too much of the trying to figure stuff out and trying to keep up with the reading, like the 300 article and the 200 articles, things that you said we need to read entirely of.
Yeah. There's after you've worked through the workbook, which I was really proud to see you went through those 2 pages. You did exactly what I asked for. I'm going to look at those again tonight and some tomorrow. But I think that once you've done that a little bit, then we do one-on-one time. It makes a little bit more sense. So I'm ready. I'm ready to do Ohm's law. I just don't want to do them tonight because I've got a history exam I've got to take tonight. So I'm kind of behind the schedule. But
I appreciate the time.
Hey, no problem. If you will text or email Melachris, do you have her contact info? Well, the email that she sent you out with the Ring Central invite for this class, for this session, just email her back and ask her, hey, can I have Mitchell said I could have a Ohm's law one-on-one sometime next week, and she'll set that for us.
All right, well, as soon as I get off there with you, I'm going to do that.
Okay, and I'm sorry again for being late, guys, but I appreciate y'all's patience.
Thank you so much.
Yeah, all right. Have a good evening. Be careful.
Uh-huh.